Good evening, everyone, and welcome to our symposium on infectious disease epidemiology. My name is Steun Bousma, and I'm a professor in the epidemiology of tropical infectious diseases in Nijmegen.
And my name is Cornelia van Duin, and I'm a professor in epidemiology at the Nuffel Department of Population Health, Oxford University. For each of us, it's a truly exceptional and amazing time. The COVID-19 pandemic has paralyzed our world, our healthcare, our government, and our society.
It's exceptional, but it's not entirely new. So in 1918, of course, there was the influenza pandemic, also known as the Spanish flu, and that in many ways was not dissimilar to today. Wave after wave of new infections with new virus variants overburdened hospitals and excess mortality across the globe. Perhaps a novelty is that now we can make scientifically intelligent projections.
Well, one may argue that making clever projections about epidemiology is not new either. Major Greenwood already plotted the number of Spanish flu patients and pointed in the UK that the rising cases really showed similarity to previous epidemics of so-called the Russian flu of 1889. Based on his model, he predicted in the summer that the UK would see a second wave of Spanish flu in the autumn or winter. During the Spanish flu pandemic, virology was still in its infancy. So the human influenza virus was not discovered until the 1930s. So what is remarkable that with so little knowledge of virology and immunology, many of the interventions we see today have already been implemented to battle the Spanish flu. Face masks were the future of the Spanish flu and were even personalized and fashionable, as you see on the slide.
Also, like today, epidemiology was really taking an impact on daily life. Patients were isolated, schools and theaters and pubs were closed, church services were held outdoors. There were also major debates, for instance, about whether it was clever to close down public transport in the midst of the war efforts. And there were also conspiracy theories, for instance, that the Spanish flu would be man-made and perhaps distributed from German U-boats as a form of poison gas. There was also disinformation that the pathogen circulated in Bayer aspirin packages. So if even conspiracy theories are not new, what is new?
Well, possibly new is that our colleagues in pharma and academia have been able to develop an effective vaccines, multiple ones, within a year after the emergence of a new virus. A great achievement when society is yearning to return to some kind of a new normal. The job is, of course, not done, not for the vaccine developers already working on the next generation of vaccines, not for the epidemiologists who can now monitor and predict how different vaccines change the pandemic shape and under what scenarios they may help best.
What's definitely also new is the unsurpassed importance of autonomy. This feeling of autonomy really determines our attitudes towards healthcare, towards society, and towards government. The fact that people resist vaccination, as some will, is not new. However, during the smallpox eradication, some populations were actually vaccinated against their will to get rid of that horrible disease. Such an approach is completely unthinkable today.
Another novelty is possibly that in Western societies like the Netherlands, we now have many generations that have never faced infectious diseases as a major threat to everyday life. By the end of the previous century, tuberculosis was successfully battled. For bacterial diseases, we had antibiotics since the 1930s, 1940s. Perhaps because of these successes, or practical knowledge on how to deal with major infectious diseases in our Western societies has blankly disappeared. Well, our grandfathers, or great-grandmothers would be astonished to see us running around with Fitbits and Apple Watches to monitor our heart rate and sleep, and yet being so clumsy in terms of epidemiological hygiene and how to prevent an infectious disease. Their major life threats.
So some say in the Netherlands that because of the COVID pandemic, we now have 17 million epidemiologists and virologists. We hope that this symposium will help some of these epidemiology enthusiasts and illustrate some of the basics of infectious disease epidemiology. For instance, how genetic epidemiology can help us to monitor the pandemic and monitor new variants emerging, or how modeling can help us to predict what the impact would be of different interventions. Tonight, we hope to stay away from some of the burning political debates. At the same time, we do hope for many, many questions, and you can ask them by the Q&A option in Zoom. It should be at the bottom of your screen. If you have a question to one of the speakers specifically, please start your question with the name so we can make sure it ends up on the right desk. Please keep your answers, your questions short so we can answer as many questions as possible. And we would like to tell you that you can ask questions until 5 p.m. tomorrow. So we will still try to answer late questions, and we will post them on the website along with the questions. Are you watching via YouTube? That means you're watching a live stream from Zoom. It also means that the speakers will not monitor the chat on the YouTube channel. So back to the program. Tonight we have young or young-ish experts of international prestige. They really can show us how the job is done in terms of infectious disease epidemiology. Their daily lives are filled with epidemiology. And with pride, I introduce the first speaker of tonight, Professor Sake de Vlas. Sake, the floor is yours.
Okay, hello everybody. Thank you so much, Teun, for calling me young and for giving me the opportunity to present something about infectious disease modeling. I tried to find my notes, but I can't. Let me check here. Yes. Okay, thank you so much. What I will do is present the basics of my research field. And actually, my background is mainly in infectious diseases of the tropics. But I've also done some work on SARS and recently also a little bit about COVID-19. First, I would like to explain a little bit about the scientific discipline we're talking about. So first of all, we have the epidemiology, which studies the distribution and the determinants of health and disease. Within this area, we have infectious disease epidemiology, and that's a special area. And the question is why? Well, that's because individuals interact with each other because of transmission. This means that by studying this, you need to have a population view. And that is also the reason why you so often see modeling transmission modeling to be part of the science. And actually, this modeling is not that much related to other modeling efforts within epidemiology. There is more an association within biology regarding predator-prey modeling.
Sake, we do not see your slides yet.
Okay, sorry about that. One way or another, everything is a little bit different. Let me do it like this. Zoom. I'm terribly sorry about this. I'm sorry, I can't find the reason. Let me see here. Ah, there it is. Sorry, it has disappeared one way or another. Share. Is it now okay, Tang?
Yes, we can see it.
Yeah, we see it now.
You can see it now, okay. So I lost my presentation mode again, but perhaps it is here. Yes, so we are now at the beginning?
Correct.
Yes, okay. Well, I'm not going to introduce myself again. So let's move on here to the field, the scientific discipline. And what I explained is that infectious disease epidemiology is special because there is interaction between individuals due to transmission. And that's why we see so much modeling. And modeling is also used in other fields of epidemiology, but not that much related. You better search for predator-prey modeling within biology, for example. That is also modeling focusing on populations as a whole. However, within unhealthy behavior research, modeling also plays an important role, especially unhealthy behaviors, because we see also interactions between individuals here, because they can influence each other by copying certain unhealthy behaviors, such as smoking. Okay, now let's have a look at an infectious disease. What we see here is an outbreak described by Jones. And what we see here is 2-3 cases caused by one. And I think everybody now knows that this is well described by the so-called basic reproduction number, R0, which is defined as a number of secondary cases caused by one primary case in a fully susceptible population. In this example, we see that R0 is about 2.5, which is, by the way, about the value for COVID-19. Measles, for example, has a much higher R0 of about 12 to 18, and SARS in 2003, of which I will explain a little bit more later, has an R0 of about 3. To this spread, we see a typical, what we call exponential growth, which is described here by this figure. It initially starts slowly, but then it starts to accelerate exponential growth. This is the example of COVID-19 in Africa. So a little bit of topics in this talk. We can use R0 for a special calculation that also quite a few of you probably have heard about, which is the critical vaccination level. So say a fraction F is vaccinated, then we will have no epidemic. As you all know, R0 needs to be less than 1 to have no epidemic, but now we have a fraction F vaccinated, so 1 minus F is not vaccinated. So R0 times this fraction needs to be less than 1. If we divide by R0, we have this expression, and if we subtract 1, we get F needs to be larger than 1 minus 1 over R0. If we use the same diseases, we will see that for measles, with a high value of R0, this threshold is 92 to 94%, which indicates why we aim for a vaccination coverage for measles of about 95%. For SARS, this percentage, even though there is no vaccine, is 67%, and for COVID-19, it has to be about 60%. So if 60% of the population is vaccinated, theoretically, the infection cannot spread. This is also called the herd immunity threshold. About 40% of the population is protected by the vaccination of others, again, theoretically. Now, let's go back to this exponential growth that I demonstrated before. This is a so-called epidemic curve. The example here is SARS in Beijing. More about SARS later. What we see here is an exponential growth in the first phase. And on the x-axis, we see the date of symptom onset. That is what you usually have in an epidemic curve. Then after some time, we see a flattening of the curve. It's not growing exponentially anymore. We have a peak here, followed by a decline. Well, this information can be used to calculate the so-called effective reproduction number expressed by RT. This is the number of secondary cases caused by one primary case at time t. So basically R0, R0 is the situation at time is 0, when everybody is still susceptible and we have no interventions. What you see here for the same epidemic curve is the associated trend in RT. This was based on a methodology by Wallinga and Teunis. And Wallinga is Professor Jacco Wallinga, the head of the modeling unit of RIVM. And an important thing we see here is that during this exponential growth, R0 is about 3. When the curve is flattening, we see that RT is going to a lower value. At around the peak, it reaches the value of 1, and then it is declining, and RT is below 1, and the infection disappears. This is what happened with SARS in China. Now I have a short recap of SARS. First of all, SARS also was a coronavirus, just like COVID-19. It was baptized SARS-CoV virus, and now it has been renamed to SARS-CoV-1 because we have a number 2 now. For SARS, the civet cat was involved as a host, and at least it used to be, perhaps it still is, a delicacy in the southern Chinese kitchen. Well, the eating was not the problem, but the so-called wet markets that we see here. And probably these wet markets have also played some role, or maybe they have played some role in the initial spread of COVID-19. And we are, of course, all looking forward to the report of the WHO delegation about this. Here you see the spread of SARS from November 2002 to June 2003. It started here in Guangdong, Hong Kong area. And after some time, it was transferred to Beijing, and from Beijing, it affected surrounding provinces. This is what happened in China. At the same time, especially from Hong Kong, there were also infections introduced in other countries in the world, especially Canada was relatively heavily affected. This was, in the modern times, the first pandemic. But if we look closer at the values, we can now conclude that it was a very minor pandemic. Over 8,000 cases with 10% dying. And that is, of course, a very clear outcome. At that time, nobody questioned about whether or not this infectious disease needed to be controlled, because a death rate of 10% is really significant. Another thing which was special about SARS is that the large majority of cases occurred in China, about 5,000. So SARS was typically a wake-up call. Around that time, there was a lot of secrecy and sensitivity about what exactly has happened in China. And we were in the situation of organizing a workshop in 2005, 2 years later, to bring together many Chinese researchers to to gather all the data, all the knowledge that they had about SARS. And in 2006, 1 year later, I was working with Chinese researchers to get a better understanding of the SARS epidemic in China. This resulted in a special issue in 2009 in Tropical Medicine and International Health. For those interested, I still have a few copies to share. One of the studies is about the pattern of RT in different parts of China. What you see here is the province of Guangdong, where SARS started. If we first look at the trend of RT, so actually R0, we see that it has a value of about 2, not really 3. It was only 3 here, only 3 for a short time. Then it dropped to a lower level and it stayed at about 1. And here it dived down to values less than 1. And what we did was indicating here by the values and the arrows, different events and interventions that have happened. And what we need to conclude is that number 6, which was the moment that the Chinese government started with a strong political commitment. There was a centrally coordinated response. So the government said, this is SARS, this is what you need to do about it. At that time, SARS was very rapidly controlled. And actually, the stringent control measures indicated by number 7, very intensive lockdown already happened when RT was less than 1. So the epidemic was already dying down. If we look at Beijing, we have already seen Beijing, but this is with the complete data. We see, of course, first of all, it started much later. Date of onset here is somewhere starting in February because it was introduced in Beijing much later. We see that R0 is around 3, as we know for SARS. And also here, at the time that the Chinese government took control of everything and was open about everything, SARS soon disappeared. And these interventions were basically isolation of cases. That did the job. If we look in Tianjin, which is a big city province near Beijing, we see a different pattern. Here, R0, the initial situation, was around 12, which can be explained by the fact that SARS was largely spreading here in hospital situations. But even here, at the time of 6, RT dropped down rapidly and the stringent control measures occurred when the epidemic was already dying down. So what can we conclude? First of all, R0 is not a fixed value. It can be very much context specific. Furthermore, RT describes the state of the epidemic and it can be useful for evaluation of interventions, but at hindsight. Now we want to have RT in real time or nearly real time, and that has some challenges. What we basically need is the number of new cases at date of symptom onset. And we also need a serial interval, which is the average duration between the date of symptom onset for a primary case versus a secondary case. This led to some challenges which are nicely described by a recent paper by Gostich et al. Because initially not a lot of testing happened. And for SARS, the situation was so much simpler because everybody who contracted SARS developed symptoms and was really ill and went to a doctor and was identified. For COVID, that's a different story. So this is, infection here is basically the thing we don't know. Then for part of the people, there is symptom onset, then they will be tested, and we have hospital admissions and perhaps later on also ICU, and then hopefully recovery. until the 12th of June, because the data were most reliable, hospital admissions were used to calculate RT. However, there is quite some delay between symptom onset and hospital admissions, and also there is a reporting delay. So that has some challenges. By the 12th of June, when there was more testing, individuals testing positive were used. And this gave an outcome which is at least closer to the moment of symptoms. But still, there is a delay of about 14 days regarding the accuracy of the calculations of RT, but it's still pretty close to indicate the current situation. Now, everything I've said up to now is about trying to draw conclusions from what has happened in the past. Now, something about modeling for prediction. And what we need is, if we want to make predictions about the impact of interventions, is that we need a mechanistic model. We need a structure of how we think a system works. And for infectious diseases, the SIR model, first about 100 years ago, it was introduced by Kermack and McKendrick. This is the basic structure that is already useful for many different infectious diseases. SIR means susceptible, infected, and recovered. So the population is divided into these three groups. And what we need here, what we have here, is a rate, a transition rate from susceptible to infected, which is governed by a transmission rate, that's the parameter. And we have the flow from infected to recovered, which is governed by a recovery rate, which is described by 1 over the average duration of infectiousness. And the multiplication of these two, the transmission rate times the duration of infectiousness, is the basic structure of R0 in many infectious disease models. Of course, this is just one model variant, the SIR variant, but we also have the SEIR, which includes an exposed state in between. This is the model we see most of the time for COVID. And the model that Azra is going to present later on is using the same system. Here we have S, we have exposed, and we have recovered, and we have here different infection states in between. Most likely, after some time, we will have an SEIRS model, because at some point in time, it's likely that recovered people lose their immunity. Furthermore, models can have an age stratification, and of course, now that we are interested in vaccination, we will need additional vaccination compartments. I quickly show this because this is about the RIVM model, which is also an SEIR model. And a special feature of this model is the inclusion of age stratification. And what is included here is a contact matrix of different age groups, where the light colors indicate the number of contacts per individual. And what you see here, for example, is children in daycare and in schools have relatively high numbers of contacts. One thing you also see, and that is a very strong feature of the RIVM model, is that this information is updated over time. The baseline was in 2016-17, but now we have updates. And in April, you can see here the effect of the intelligent lockdown, in February, the effect of the lockdown that we have right now. Of course, we can add more realism, more detail to models, and I present here a few. First of all, we have the possibility to include stochasticity in the model. The models we have seen so far, including the RIVM model, are deterministic models. Stochastic models allow for chance effects and also the possibility to have more detailed durations. Furthermore, something I personally and my team work on a lot is stochastic individual-based modeling, which is using computer programs in which you have individuals with different characteristics. And these individuals differ from each other, just like individuals in the population. So we can allow for heterogeneities, which can be very important to include in models. It also offers the opportunity to have so-called superspreading events included in your model. As I said, this was a specialty, and the work was pioneered by Professor Emeritus Dick Habema, my promoter. This is another model which we are currently working on, and it allows for geographic stratification. And what you see here is different clusters, you could say villages, neighborhoods, and they are combined into superclusters, for example, provinces. And with this model, we were interested in a strategy focusing on geographic areas. This paper recently came out in Scientific Reports. But now we are working on it to use it for studying questions regarding mobility and mass gatherings, funded by ZonMW. Here I have an illustration of the impact of heterogeneity and why it is important. This was based on an example of 10,000 individuals in just 10 clusters. My colleague Luc Koffing, he is a bright assistant professor in my team, made these calculations. And what you see here is that if we have observations of an initial exponential increase and we assume homogeneous mixing, then we could have this pattern which corresponds to an R0 of 2.5. However, in reality, most likely there will be heterogeneity in mixing. And the same pattern can then be described by a model which has an R0 of less than 2. And this is what you often see. Initially, the epidemic spreads in those individuals and in those communities where it spreads most easily, and R0 is often overestimated initially. Another factor that I haven't mentioned is assortative mixing of, which is also playing a role here, that people with many contacts may cluster in the same communities. That's another factor that also plays a role. If we include that, then the same epidemic will even be less intense. So this is a factor that sometimes is important to take into account. Now, a few words about uncertainty. Never believe a model that just provides you one answer. Uncertainty always needs to be included. And there are many sources of uncertainty. And I have used again something that Jaap van Dissel has presented yesterday to our parliament. And this is about what we may expect about the trend of COVID given different interventions and given the assumptions about the effect of the vaccine. So uncertainty, first of all, comes by the future policy. Are we using the same measures as today, or will we have some relaxation? Furthermore, the behavior of the population is likely going to play a role. Are people obeying to the same rules in the same way, or are they going to not to comply that much anymore? Furthermore, another factor to take into account are several biological parameters. And for example, if the vaccine, we still don't really know that, is only affecting the development of disease, or also affecting transmission. And there are many other biological parameters playing a role. Another aspect that could be taken into account, but it's not part of the RIVM model, are chance effects. You need a different model for that. But now with the high numbers of individuals, chance effects are not so important. But at the beginning or at the end of epidemics, it may play a more important role. And furthermore, of course, model structure plays a big role, the type of model. This is just one model, and sometimes it would be good to also focus on other models. Now, my final slide, I have a few concluding remarks. First of all, the past year has shown that models are very influential for policymaking, and many decisions about lockdowns and relaxations have been justified by modeling. This makes it also important to be transparent about the models used. And I respect the modelers at RIVM highly, but the ideal would be to be open about everything: model code, data used, decisions made, etc. I understand that it is difficult because the RIVM model relies heavily on data that have privacy issues. But would it perhaps be a nice compromise to have a kind of interactive peer review with other modelers to discuss the ins and outs of the model, to perhaps provide some feedback or some suggestions, perhaps find errors, or just to give a pat on the shoulder and say, well done. Another thing which is important in the modeling is that we need more attention for validation. How well were the previous predictions? And also as part of the validation, to compare outcomes with other models. Secondly, modeling only provides part of the evidence for policy making. Other factors like economic considerations, social considerations also play an important role. And that's okay. Politicians in the end decide. However, if I look at the Dutch vaccination strategy, I'm pretty sure that no model would support the fact that healthcare personnel is vaccinated before the most vulnerable, as the Gezondheidsraad has advised. And furthermore, also suspending flights to and from UK to keep the British variant out of the country is also something that has certainly not been supported by modeling. Furthermore, if we use models to predict the impact of interventions, first it is essential to estimate the behavior of the population that is involved regarding these interventions. And that is often quite a challenge. So exactly the same measures in the first wave and in the second wave will have a different impact, simply because the degree to which the population is responding to these interventions. Finally, in making predictions regarding preventing disasters, preventing disease outbreaks, we always have the problem of the prevention paradox. Because we hope that these bad situations do not appear, so that people, but as a consequence, people may say, well, we don't see anything about this, so what's the problem? Well, that is something we can deal with, but for infectious diseases, I consider this to be a prevention paradox plus. Because of this exponential increase, everything happens so quickly that the disasters are relatively large, and the efforts necessary to control them are also going to be major. This is what I wanted to say. I thank you very much for your attention.
Thank you very much, Sake.
And sorry again for the problem with sharing my material.
No apologies needed. Sake, nice also to illustrate in your last slide that although we are not giving a politically charged webinar, it's impossible to stay away from some of the complexities of interpreting models. There are some interesting questions coming in through the Q&A session. I will reserve them to the final discussion. I welcome you to ask more questions. And now it's my pleasure to welcome the second speaker of today, Dr. Bas Oude Munnink from Erasmus MC from the Viral Science Group, who will talk us through some of his work and some of the basics of genetic epidemiology.
Thank you, Teun, for the introduction, and thank you for inviting me here to give a talk. So I will today talk about the genomic tracing of SARS coronavirus 2 by using whole genome sequencing. And just a little bit as background, a little bit reflection about coronaviruses, because we know already some things about coronaviruses. So coronaviruses are already well known, as also previously described in the previous talk. So the coronavirus is part of the very big family of Coronaviridae. And here on the right side, you can see already a phylogenetic tree, which is trying to reconstruct the relationship between the different viruses. And we can see that this group of viruses consists of viruses which can be detected in quite a different host range. So there are up to now 7 known coronaviruses which can infect humans, but they also can infect, for instance, bats or carnivores. So it's really a wide host range of this big group of viruses. And the SARS coronavirus is an RNA virus of around 27 to 32 kilobases. And next to the SARS coronavirus and SARS coronavirus 2, which are really causing big outbreaks, there are also 4 coronaviruses which are causing the common cold. And these are called NL63, HKU1, 229E, and OC43. And perhaps in the past they have caused big outbreaks, but at the moment they're just causative agents of the common cold. And then there are 3 coronaviruses which are more pathogenic. And these are then the MERS, SARS, and SARS-CoV-2 virus. So just to explain a little bit about SARS coronavirus 1, I will keep this short because also in the previous talks it was already covered for quite some extent. So SARS-CoV-1 was an emerging infectious disease responsible for the first pandemic in the 21st century. But as opposed to SARS coronavirus 2, it was not widely spread across the globe yet. So it was first identified in 2003, and there have been no more reported cases until 2004. And mainly in Asia, this virus caused quite some problems. And in total, there were over 8,000 confirmed cases, and indeed with a case fatality rate of around 10%. So this virus was way more lethal than the SARS coronavirus 2. And at that time, this virus could still be controlled by quarantine. But then later on in 2019, we first discovered SARS coronavirus 2. It was first detected in December in 2019 in China. And it was linked to, in the first case, to a wet lab market, where they sold mainly seafood. So after the detection of this virus, they were pretty fast in identifying the causative agent of this virus. And although the zoonotic origin of this virus remains to be determined, so there have been several hypotheses about pangolins playing a role, or bats or snakes. We still don't know yet where this virus actually originated from. So the idea we have now is that it occasionally came from bats, but that we need some sort of intermediate host before the transmission or the host germ towards humans was made. And also in recent experiments, we could see that bats, monkeys, hamsters, cats, ferrets, rabbits, lions, and even mink can be infected by this virus and can also shed the virus. So it seems to be that some sort of animal was present at this market or was present somewhere else in China, to which the virus was transmitted from bats and then later on to humans. But this host range is pretty broad, so it's quite difficult to determine what was really the intermediate host. But a lot of research is currently ongoing trying to identify this intermediate host. Just to give a little bit background about how we can use whole genome sequences for instance, for outbreak detection or for other purposes. So we know that all viruses change over time and that they just mutate. And also I will finish that later on in my talk. I'm talking a little bit about the variants of concerns and the new variants which are popping up at the moment. So we do expect already the emergence of new variants, but most of them will be harmful for the virus survival, and they will have no impact on the function or structure of the virus. But it's just something that simply happens. Viruses replicate and they make mistakes in their genome. And through that, you can see some changes in the genome of the virus. However, sometimes this can also result in a major advantage of the virus. So it can lead to increased transmissibility, increased severity, And it can also influence the efficiency of vaccines and therapeutics. Although normally you would need quite some changes before this really has an effect on the vaccines. And the mutation rate of SARS coronavirus 2 is relatively low compared to other RNA viruses because it has a proofreading mechanism. So there are not too many mutations occurring in the SARS coronavirus 2 genome compared to other RNA viruses. However, the chances of mutations, of course, increase with the frequency of humans and animals which are being infected, because every time the virus replicates itself, it can incorporate a mutation. And the more the virus can replicate, of course, the more mutations you will see in the genome. So that's also why we can use now whole genome sequencing for outbreak investigations. And this is all mainly due to the Chinese collaborators who already identified the first sequence and shared the first sequence on an international database on the 10th of January. And by now, over 500,000 sequences have been generated and shared. And this is really a new thing during this pandemic. Because, for instance, during the previous epidemics, there were only a few amount of whole genome sequences available. And now we got a very rich database of sequences to which you can compare your own data and trying to see, for instance, where the virus came from, how widespread the virus was in a country, for instance. Is it really different, and how different is it from what we've seen before? And we can use it for outbreak investigations. Like, is it likely that there's an outbreak going on at a certain scenario, or is it perhaps individual introductions? And we can determine if it's part of a transmission cluster or not. So to do whole genome sequencing, we now use an amplicon-based sequencing approach. So it's quite technical, but I'll try to explain it very shortly. So we perform two different PCRs with overlapping amplicons. So we do it in two separate tubes, which we combine later on in one tube. And then we can perform already the library preparation and sequencing. And for that, we used a method which has been described previously for Zika virus and other viruses. And you can directly get full genome sequences and sequence them from clinical isolates. And we do that now using the fieldable nanopore sequencer. So it's really handheld, and you can take it almost everywhere and perform your sequencing there on the spot. And also for a little bit more high throughput, we got the bigger machines where you can run 5 flow cells at once. So you can sequence up to 96 samples per flow cell, so you can almost sequence 500 samples overnight. So just to briefly demonstrate the sequencing in the field. So I've been to China 2 years ago also to do some sequencing there on the wet labs. So we visited there indeed the poultry farms, and then we tried to find out, mainly for the avian influenza surveillance, what viruses are circulating there. And then we were also able to bring our own sequence machine and perform the sequencing on the spot. And we did a mobile trip to Brazil to sequence Zika virus. And there we drove around with a minivan, and we were able to do the sequencing and the library preparation inside the van, and also the data analysis we performed inside this minivan. And then even last year, I went together with Emmanuel Munger, a PhD student who went to Suriname, and we also did some sequencing there on the spot. So we just bring our laptop, reagents, and we can do the sequencing there. So after the sequencing, we have to do, of course, some sort of bioinformatic analysis. So after one sequence run on the fieldable sequencer, there are around 12 million sequences which are generated, which is around 10 gigabytes of processed data. So the raw data is even close to half a terabyte, which is being generated after each sequence run. And by now we've performed around 300 sequence runs. So we got quite some sequences available and quite some data. And what we then try to do is, because we amplify all the different PCR products, we try to reconstruct the viral genome. So we perform an alignment and try to reconstruct how the entire genome is looking like. So then per sample, we get a sequence of around 29,500 bases. And that we try to compare to each other to see how they are related to each other. So this is then how a multiple sequence alignment looks like. So here's again, for a few samples, you can see the whole genome sequence of SARS coronavirus 2. And then every black line presents a mutation or a change in the genome. And you can see that the changes are still very limited. So for instance, the second one only has around 8 differences compared to the first one. And that's based on the entire genome of almost 30,000 nucleotides. And this multiple sequence alignments we can then use in phylogeny. And in the phylogeny, we try to reconstruct what's the most common ancestor of these viruses. So how related are they? So you can also see this in this very different annotated tree. So you can use it for mating. In big lines, you can try to determine their relationship. So you can, for instance, see if they are most likely sisters of each other, or they are somewhat further family related, or they are perhaps even further away, and it's your grandmother or your neighbor, or it's really further away from the original the ones. So that's how we try to visualize how related these viruses are to each other. So in the beginning of this outbreak, thanks to the quick sharing of the genome by our Chinese collaborators, we were able already to set up a protocol. So we were already prepared before the first corona case in the Netherlands occurred. And we had the protocol up and running. And we could use our rapid whole genome sequencing also to really use it this time for informed public health decision making. So after the first phase, the initial testing was done of travelers according to the WHO and ECDC case definitions, we got the first SARS coronavirus 2 infection detected in the Netherlands and confirmed on the 27th of February, and additionally one case later. And then we were able to get already the first 2 whole genome sequences of these samples and analyze these sequences by February 29th. So within 2 days after the first detection of the virus, we were able to get the whole genome sequence of these 2 isolates. And that's now depicted here in this phylogenetic tree. And what we could see already is that these 2 cases were not related to each other, and most probably represented different introductions from Italy this time. So here we could already say something about the relationness of these viruses. Although this virus was only circulating for, the estimates are around 2 to 3 months globally. But then already we could see some differences in the genome. So we could differentiate between if they are from one source or from different sources. So we also continue with the sequencing during the exponential growth phase. So then we still sequence every positive case which we detected in the Netherlands. And here we could see that the sequences detected in the Netherlands were already quite diverse and revealed the presence of multiple co-circulating sequence types, which clustered also differently in the phylogenetic tree. So at a certain point, it was very difficult to try to interpret these trees because most of the sequences were derived from the Netherlands. So everything seems to be circulating in the Netherlands, while they most probably represented different introductions. But we could also see that, so the names here now in red are cases with travel history to Italy, while the cases in blue did not represent any travel history. We could see that there was really an increase in COVID-19 patients, and there was also increase in the affected geographical regions. So not only in North Brabant, but also we could find it in Limburg and in Utrecht and in several other provinces in the Netherlands and also in Overijssel. And we could also see some local clusters occurring. And this then provided some support for the increased movement restrictions we put into place, because we could already see based on the genetic signature that the virus was most probably way more widely spread than we anticipated on in the beginning. So what we also did during the last year is trying to determine the geographical signature. So we try to relate it sometimes to, can we identify where the virus is coming from? So for instance, after the summer holidays, one of the main questions we got is there now an increase in the amount of coronavirus cases due to people traveling to Spain or to Italy or to some place we go to have holidays, or if it's just ongoing circulation within the Netherlands. So we try to determine the geographical signature of that movement. And we try to monitor significant changes in the genome and try to see if perhaps viruses get more virulent or more pathogenic, although this is still quite a challenge. And we did quite some outbreak investigations. So for instance, we did a big study in healthcare workers in 3 hospitals in the south of the Netherlands, where we could find that there was not too many or not a lot of transmission within the hospital, but most likely that most healthcare workers got infected in their social life or in their private life. So that's also something we learned during this outbreak, is that sometimes you think clusters are related to each other, or perhaps you think there's a big outbreak in a hospital, but it might also be that people just got infected in the community. And at the time, also healthcare workers got tested with priority. So it's not then that surprising that you find it more often in this population. We also did a lot of outbreak investigation in nursing homes and in slaughterhouses, but also in gyms, schools, in the food industry, and in mink farms. And I will tell a little bit more about our outbreak investigation in mink farms. So we already know that coronaviruses are circulating in animals. And also because SARS coronavirus 2 was first detected on the seafood market and a live animal market, it was suspected that animals might have played a role in the emergence of this virus. In this market, I have to say that a lot of animals were tested, but actually no animal tested positive for SARS coronavirus 2. But the virus could be identified in environmental samples. So it could be that the virus was still on the market, perhaps spread from human to human on these markets rather than that it came from an animal source. And we have seen that several other animal species are also susceptible for SARS coronavirus 2. And examples has been described already from dogs, cats, lions, and tigers. And then we also detected SARS coronavirus 2 in mink farms in the Netherlands. So this was the result of an early warning system where they saw an increased mortality in 2 mink farms on the 19th and the 20th of April. And here, for instance, in one farm, 12,000 animals. Out of the 12,000 animals, 285 died. And in the second farm, it was a little bit less, but also a substantial amount of animals suddenly died. And then it was first tested for all other pathogens, and then at a certain point also for SARS coronavirus 2. And then they were found to be almost all positive for SARS coronavirus 2. So in the end of the year, the latest update was that there were 67 mink farms in the Netherlands infected, and several other countries reported also outbreaks in mink farms. And we tried to use whole genome sequencing, trying to see how the virus spread from these different to these different farms. And here we also again used the mutations in the viral genome to try to track and trace where the virus is going. So this is a slide I used from was also used by Jaap van Dissel in the briefing of the Parliament, and there he also tried to explain how you can trace these mutations. So, for instance, in humans, you can see one specific mutation occurring, which can then be perhaps transmitted to mink. And then if you see several mutations popping up in mink, and you see it's transferring back to an employee, for instance, of these mink farms, you can determine that the virus has spread from humans to mink and then from mink to humans. So it's also something we investigated in the Netherlands. So when we look at our mink sequences and our mink farm sequences compared to all other Dutch sequences, we can see that now in a big phylogenetic tree over here. And we could see that there were only 5 different mink clusters, mink-specific clusters. And we could see that the virus spreads most probably from mink farm to mink farm without the necessarily of being having a human in between. So we could see that there were 5 different jumps from the human population to mink, and then later on a spread from mink farm to mink farm. And also what we observed is that there was quite some divergence compared to what we see in the human population. So the branches of these trees are very large, and we could see that the virus was mutated quite a bit in these animals. But mainly what we saw is that there were 3 main clusters with 67 mink farms. And one thing to also note is that although we did not find this virus a lot in the surrounding of these mink farms, it was an increased risk for mink farm employees, because we could see on the first 16 mink farms that 68% of all tested farm employees were positive either by PCR or serology. And I would say either the virus was detected in these individuals, or they had an antibody response against SARS coronavirus 2. So it's highly likely that they were infected with SARS coronavirus 2 from these minks. And then to show a little bit more about the proof of mink to human infection. So we used phylogenetic analysis to try to determine this. So by using phylogenetic trees, we could see that they cluster together with the sequences derived from the minks from these same farms. But we could also use the timing of infection to prove the direction of the spread. So we could see that after we found SARS coronavirus 2 in these minks, around 2 to 3 weeks later, we found employees positive. So then it's really indicative that most probably the virus first got introduced in the minks in these farms, and then later on the farm employees got infected. And here in blue in the phylogenetic trias are all the human samples. And we have to take care a little bit because we don't know how exactly the spread went in these different farms. So it can be that the virus jumped from mink to human and then later on from human to human. Or it can be that several employees at this farm actually got affected by mink. But we can see at least that one of the employees got the virus from the mink, and how it later on spread is always difficult to determine because they also, most of the times, live in one family. So it can also be transmission within the family. And then as last topic, I wanted to address a little bit the variants of concern. So there have been a lot of media attention, which I'm sure all of you have heard in the news the last times, that there are some variants now of SARS coronavirus 2, which might be more deadly, more pathogenic, and more easily transmittable. And there are at the moment 3 variants of concern. And I realize this is a very busy slide, but this is just to indicate what we're trying to summarize now and what we know about these variants of concern and what we don't know about these variants of concern. So what we do know is that there are at the moment 3 main variants of concern. And according to at least what we are being asked by the WHO is try to prevent the stigmatizing names. So I try not to call them the UK variant and the Brazilian variant or the South African variant, but we just try to give them a name. But what they all have in common is that they have some key mutations in the spike protein of this virus. And they are quite some mutations compared to what we see in the general population. And for all of these 3 variants, we can see that there is an increase in transmissibility. So it seems to be more easy to transmit this virus from one people to another. And most probably this has to do to either a longer duration of infections or a higher viral load during the infections. But the disease severity is not that obvious yet. So we don't know too much about the different outcome of the disease. But there are some reports that the neutralization capacity might be less. So it might mean that you might get reinfected by one of these strains, although you had already a previous coronavirus infection. And also some impacts on vaccine has been described, but this seems to be not too major at the moment. And then one of the hypotheses on how these variants can arise. So with 2 of the key mutations which we see in all variants of concern are the 484 and the 501 mutation, which is present in the spike protein. And there has been a case report described in an immunocompromised host who received therapy, where they could see that when they followed this patient in time, so they sequentially also sequenced the virus from this patient, they could see mutations popping up, also in the spike protein and also in other parts of the genome. And these were also specific mutations which you can also find in the variants of concern. And also when we look at our own data, so we also got 3 immunocompromised patients which we followed in time, we see similar mutations showing up. So again, we also can find the 484 mutation, and also the specific deletion is also found in 2 out of the 3 patients which we could find in our hospital. It seems that immunocompromised patients might indeed be in these patients, there might be a variant of concerns occurring, but it can also be that it was just a simple underrepresentation of the sequencing effort, which is done at the moment. Because, for instance, in the UK, they sequence more than 10% of all positive cases, while in Africa, we have really no clue what the genetic diversity is of the SARS coronavirus 2 now circulating there, for instance, in Tanzania or in Sudan or other countries where they don't do any sequencing. This is a slide I got from my colleague Richard Molenkamp. So here we try to, in the Netherlands, try to follow up the variant of concern in time. And this is now, for instance, the UK variant. And we could see that in the different week numbers. So here we started around 2021. We saw a gradual increase of these variant of concern. And by now, it's not really based on modeling, but just by doing a specific PCR, where you just try to randomly monitor what's going on. So we try to sequence, I think it was 4,000 SARS coronavirus 2 cases, where you then try to identify is this a variant of concern or not. And we could see that now in the latest week, around, in all different sites which are being tested at the moment, around between 60 to 80% of the virus we find now is the variant of concern, and then the UK variant. So it does seem to have some sort of advantage over the other variant, and it seems to be taking over also the wild type strain. So that's what I wanted to share with you today. And of course, I wasn't able to do this work by myself. So I'd like to thank a lot of other people who were involved in the studies, and also all labs who contributed by sending their samples to the EMC for sequencing.
Thank you, Bas. There's one question I would like you to answer now, and then we move to the next presentation. One question is, when do you, check who asked the question, when do you actually call a variant a variant? How much variation does there have to be?
That's a good question. There's not really a specific rule. So they try to look at specific mutations in the genome. So if you find an interesting mutation in the spike, it might already be enough to call it a new variant. But there are not really clear rules. So we're now discussing with the WHO also to try to set some definitions for that, because people can call it when they want to call it a different variant.
Thank you very much. So with that, I'd like to move to the third and last speaker of this evening, Azra Ghani, professor at Imperial College. I'm a big fan of her malaria work, but today she is going to talk about COVID-19, and also with a specific focus on what we can expect from vaccinations. Azra, the floor is yours.
Thank you very much, and thank you for inviting me to speak tonight. So I'm really going to try and focus on what does the future look like for COVID-19. And I'm sure you're all aware of the current state of the pandemic, many cases and deaths, and this is probably just the tip of the iceberg, but particular severe epidemics occurring in Europe, as you'll be experiencing, in North America, Latin America, and South Asia. And interestingly, of course, other areas of the world, particularly Southeast Asia and Australasia, that have done somewhat better in controlling the epidemic. And everywhere is experiencing what we're seeing as these waves of infection, which are really quite difficult to interpret. But the reason for this pattern is a combination of two things. First, of course, as cases start to go up in any place and the hospitals start to fill up, then both social restrictions come into place, both those that are implemented by government, but also, of course, people change their behavior. And alongside that, what we're seeing is build-up of naturally acquired immunity in subgroups of the population, that then means that the epidemic starts to appear to decay away again, sometimes with no change in behavior at all. And this is exactly the pattern we saw back over a century ago for the flu pandemic, the 1918 flu pandemic. And without vaccination, what we'd expect to see is these further waves and a dampening of these waves over time as immunity builds up across the population. But of course, we have the vaccines, which is fantastic news. And I won't go into detail, but there are, of course, many vaccines out there. These numbers are changing all the time. What we do see is that we've got very highly effective vaccines, and this really was a pleasant surprise for most of us working in this area, and the speed with which they have been developed and are now being implemented. We've got some great new information coming too. For example, today Pfizer released a report demonstrating the impact that their vaccine is having in Israel alongside the government, and showing that it actually does appear to be preventing asymptomatic infection and therefore blocking onward transmission. And that will be a great aid in terms of trying to bring the pandemic under control. We also know that it's providing additional protection against the more severe outcomes, preventing hospitalization and deaths, even in the most vulnerable older age groups. And we don't know how long it lasts yet, but evidence from a similar vaccine for the MERS coronavirus suggests it should last for at least a year. And of course, boosters could be given to prolong this protection. So we've got great news on the vaccines, but as we've just heard, we also have these variants of concern. And there is evidence that some of the vaccines may not be as effective, particularly against the South African and the Brazilian variants. They do seem to be so far highly effective against the UK variant. But again, science is hopefully trying to keep on top of this and keep ahead of the pandemic. And many scientists are working very hard to change and modify these vaccines so that they can address these new variants of concern. And these can be done quite quickly, particularly with the new technology provided by the mRNA vaccines. So what does this mean in terms of the impact the vaccine is going to have? What are we going to see in the coming months and years? Well, vaccines, as Sarka has already explained, provide protection not just through the direct protection of those that are vaccinated, but also indirectly through this so-called herd immunity. So the question that often comes at the moment is, well, all our high-risk groups will soon be vaccinated. When will the epidemic be over? And one of the issues, of course, remains is that even with these highly effective vaccines, there will be populations in which it doesn't work. So, for example, if the efficacy is 90%, that still means 10% are susceptible to infection. And on top of that, not everybody is likely to take the vaccine. And the most recent survey I looked up from last week suggests there's 20% vaccine hesitancy in the Netherlands. Hopefully this will improve over time. We are certainly seeing an improvement in the UK as the vaccine rolls out. On top of that, vaccines are not yet recommended for children. Studies are underway, but this remains a large portion of the population, 20%. And transmission amongst children does seem to be slightly more effective with the newer variants, the variants of concern. And if you combine all these numbers together, that means that whilst we can have a large proportion of the population protected, it is quite unlikely in the near term that we are going to reach these herd immunity thresholds that Sarka has explained. On top of that, the new variants, unfortunately, appear to be more transmissible and slightly more higher severity. And when you factor that into account, the basic reproduction number is probably closer now to 4. So we're unlikely to achieve the high levels of effective coverage needed for herd protection. So what does this mean as we start to introduce a vaccine? Well, we can use, as Sarka's explained, mathematical models to explore the likely trajectories, and best are models, of course, that are fitted to the epidemic to date. I should stress that these are projections, scenarios. They are not predictions of what will happen, because so much of the future, even in the near term, depends on the actions that are taken. So on the bottom left, you can see an example fit. We've been doing this globally for all countries. That's an example fit of a model to the reported deaths in the Netherlands up to the current time. And alongside that, as Sarka's explained, we try to estimate this R number, the reproduction number. And that is shown in the right-hand panel. And here I'm distinguishing between two different values of R. The grey bars are the reproduction number, taking into account the social restrictions and interventions and behavioural changes that are currently in place, but excluding both natural immunity and the immunity in the future that could be induced by vaccination. Whereas the blue line is showing that same value, but also with the associated population immunity and hopefully in the future vaccine-induced immunity. And you can see that as the epidemic has progressed, particularly during this second wave, there's been a slight divergence of these two lines in that bottom right-hand panel, and that is reflecting the fact that some of the declines in the epidemic will be occurring due to natural immunity, not just to social restrictions. And so our aim as we introduce vaccines is to try to keep that blue line below 1, because that would mean that the epidemic will no longer take off. But we want to allow a relaxation of social restrictions. So first off, if we just put in a very dummy scenario, we could be quite optimistic. And I've given some examples there of reasonably plausible parameters that we could put in for vaccine introduction as the rollout continues in the Netherlands, much as it has started. And this is, of course, assuming some optimistic things, for example, about vaccine acceptance. So if we just put it in and assume that transmission carries on at the current reproduction number that we estimate, which is around 1.4, then what you see is a very rosy prediction that vaccines will be introduced and the epidemic will just decline away. Why is this wrong? Because in this very simple scenario, we haven't allowed the reproduction number to change. But of course, as we start to vaccinate the population, what we want to do is to relax the social restrictions that are in place, go back to a more normal lifestyle. And inevitably, as we increase the contacts that are occurring across a population, then that is going to lead to a higher underlying transmission rate. So to explore this, we can start to use the models and explore different time points for relaxing this reproduction number. And that's shown in the top right-hand panel by the pay grail line. You can see this sort of steps upwards. And here I fairly carefully calibrated the model to try to keep the blue line approximately at that threshold level of 1. What these actually translate to in terms of lifting of the social restrictions is actually quite difficult. And that's why epidemiologists are proposing that as we come through the epidemic, as the vaccination rolls out, we don't suddenly lift everything in one large go. That will likely result in another large epidemic occurring, but rather we take things gradually step through lifting of restrictions, measuring what's happening, and then at the point where we're confident that the reproduction number is remaining below 1, we can start to add another layer of lifting. So this is what we call a sort of cautious management approach. And as you can see in the bottom, what that would lead to in terms of impact, and this is the impact on deaths, is a sort of gradual waves downwards. We might start to see some increases for a while, then the vaccine rollout that is continuing will do some of the heavy lifting on transmission and push things down again. Of course, challenges remain in doing this, and there are always risks as we come out of a period of restrictions. We do need high vaccine acceptance. We do need to increase that everywhere, and ideally we really need to get over 90% of the population being vaccinated. And also it remains unclear whether it is going to be possible, even with these highly efficacious vaccines, to completely lift all the social restrictions in place. Alongside that, we need to keep in place our basic public health measures. Case isolation is really critical, enabling people who are ill and test positive to isolate and not transmit on infection could have a really major impact. And of course, keeping all the surveillance systems in place to look for tests and to monitor for new variants. So of course, the Netherlands and all countries will not be in isolation and will be subject to the risks of the global situation. And that's why you will often hear that we are not all safe until the whole world is vaccinated. So what is the global situation likely to look like? Well, I've sort of laid out a best case scenario, partly because of course, us modelers are often told that we're constantly sharing bad news and worst case scenarios. So here's a best case. The vaccines continue to work against the circulating variants in the short term. That is a concern that many scientists have, but of course we can try and work to circumvent that. And then it is very likely that a new generation of vaccines could be introduced perhaps as early as autumn this year. And that could help us to prevent any emerging epidemics from these new variants of concern. Critical, of course, is the supply, and you've seen a lot about this in the newspapers. Supply has increased and improved in very recent weeks, and indeed the restructuring of the Pfizer plant is going to help enormously for Europe. And I do think if we can work together, perhaps get away from some of the issues of nationalism, then a large part of the world can be vaccinated. And I think the most optimistic scenario is that, unfortunately, most of the countries, the high-income countries that have made the deals with the pharmaceutical companies are those that are likely to benefit first. And I've put down some areas that are likely to be fully vaccinated by the end of 2021. Alongside that, of course, there are many lower and middle-income countries that don't have that access. The COVAX facility is in place and will be providing enough for 20% of the highest risk populations. Hopefully, continued advocacy can enable us to increase that share. And of course, we need to work towards limited vaccine hesitancy. And I think that is improving globally as well. Under that best case scenario, then it may well be that at least in the high income settings, the majority of social restrictions can be eased nationally. And it may be possible to have international travel resume with, again, restrictions likely to be in place. So looking to the future, it's what we have learned is it's really very difficult to predict the future with this. Things change almost daily, data updates, but also things like the new variants emerge and set us back. So I think the future is going to be an uncertain one. the virus is extremely unlikely to be eradicated. And what we're going to have to do is work out a way to live with this COVID going forwards. And through that, there needs to be debate with the politicians, but also with the wider public on how to manage those risks. That will involve a consensus on what is an acceptable level of ongoing circulating virus. And that translates, of course, unfortunately, into ongoing hospitalizations, and people will likely continue to die from this disease. It needs to be managed in the context of its impact on healthcare, impact on other health conditions. Many healthcare systems are overwhelmed at the moment, and that is having a consequent impact on health elsewhere. And it needs to be balanced against the economy and livelihoods. And these are often put up as competing priorities, but actually what we're seeing is that countries that manage their COVID have also recovered economically much faster. And finally, there was, of course, the debate on the individual's role and societal freedom. And these all come together in how we move into the future. Over time, it's likely that the virus is going to become like a seasonal virus, much vaunted like flu, but there are things that are different. And in the meantime, the timescales for this are quite potentially quite long, and we need to try and do our best to continue to drive down transmission and minimize impact, whilst also trying to open up society. So I'd just like to acknowledge the work of the group, and much of the work on the vaccines I've presented here has been undertaken by the people named here. I've put a link here to covidsim.org. This is an open access interface to our modeling, and you can run as many simulations as you like using that interface. And there's an associated YouTube video which explains the steps to doing so. And some of the topics I've covered today are also covered in that news item. And finally, all of the science reports, the code indeed, and then the public resources are available at our website. Thank you.
Thank you, Azra. And now I would like to ask all the speakers to switch on their camera. And I'll start with the first question to you, Azra, and it's a combination of a question of Justus and Bert. So the recent variants seem to increase the herd immunity threshold even further. So question is herd immunity still a realistic goal, or should we rather focus on protecting risk groups, perhaps with an annual booster?
I think it's going to be a combination of both. In the short term, I don't think we'll get to herd immunity for the reasons I've already outlined. The focus has to be on protecting the most vulnerable, and that is why the prioritization has been agreed in the way it has. And I believe the Dutch are following very much the same as is recommended by WHO. Herd immunity, I think longer term may be achievable, and that will be both an increase in willingness to take the vaccine, improving the vaccination, and just really getting everything in place to drive down transmission.
Thank you. Sake, also a modeling question to you. A question from Ronald and from another Bert, different Bert. So is there a best model, or do you have different models that fit different scenarios? And the question is, why does RIVM use a deterministic model?
There is certainly not a best model. One model can be better than another one, but different models give different viewpoints. I think the best thing is a combination of models. I'm a member of a modeling consortium, and there are several model consortiums, and different models working on the same topic. If they give the same insights, then you probably have a best model. So I think that is a very important thing, not relying on just one model. Why is the RIVM model deterministic? I think this is historical. This is the model they had, which was used for influenza, I believe, and it's now used for COVID. And stochasticity, like I said, is mainly an issue at the beginning and at the end of an epidemic, but now the numbers are so high, it's not that important. So I think it's also fine that it works like this. But perhaps if we focus on future situations where we want to know about if we manage to get COVID to very low levels and we want to do something about the impact of reintroduction from other areas, then the stochasticity may become more important, and it would be wise to try other models that can deal with that.
Thank you. Then a question to Bas from Amiri. How concerned do we have to be about the super mutant B1525?
It is quite concerning, like all of the three different variants of concern, but also a lot is still unknown. So it seems that still the vaccines can be effective against these variants, but it seems to be spreading more easily. And I haven't seen any reports yet that it's causing any other clinical outcomes. So I'm concerned about the fast spread of the virus, but I don't think it will really change a lot. We can still try to prevent it by taking the measurements we do now. So keeping the social distancing, trying to work from home, and all the other things the government's advising us to do. So that should still be working, but it is concerning that these mutations start to occur this early in the pandemic.
Thank you. So another question also about concerns, but slightly more general. And I think I'll start with you, Azra. What potential pathogen, what kind of problematic characteristics keeps you awake at night? And that's a question from Serge.
Yeah, it's a very good question. This is actually keeping me awake at night enough right now. There are two factors. There's a combination of transmissibility, something that can be transmitted even more easily. Unfortunately, this is already quite transmissible. And then there's severity. And what we saw, for example, with the original SARS is it was more severe in terms of a higher case fatality ratio, but all of the transmission was occurring after symptoms. And that's really important because they were quite severe symptoms. So transmission initially occurred mostly in hospitals, but once practice was put in place to stop that, then it was relatively easy to control. What we have now, of course, is something that is quite transmissible from asymptomatics. So that makes it much more challenging to track down all infections. And actually has a reasonably bad severity. I mean, we initially estimated a 1% fatality ratio for all infections. That seems to have played out, pretty much stayed the same over the course of the pandemic. That is in line with the worst case planning that we were always looking at in terms of pandemic. So of course it could be worse, but we don't have any historical evidence of things that are much worse than we have now.
Is there anyone else from the speakers who wants to add on this? Are there other characteristics that keep you awake?
No, I tend to agree about this. This is one of the worst examples you can imagine. If it's the combination of these asymptomatics that can spread it, or the spread is already before people become symptomatic, and that is making it so dangerous. Severity, of course, a more severe infection leads to a higher death toll, but it also leads to more clarity. And for the people to follow the regulations, it's more acceptable. So this is somewhere at the level of where it is most likely most dangerous. So I agree with Azra about this.
Thank you. Bas, you can add to that, but I also have an additional question to you. So the question from Gert is, will we be in time to still discover the origin of SARS-CoV-2? And perhaps I can add to it, why do we actually need to know the origin of SARS-CoV-2?
That's a good question indeed. I'm not sure if I think we can still detect the origin of SARS-CoV-2 because we haven't found it yet. So it should just be present in some sort of animal reservoir. And we simply haven't found it yet at the moment. Although it can also be that it directly jumped from bats to humans, for instance, but that's a little bit less likely. And the reason why we should be concerned is that, of course, this is not, I think we all agree on that this will not be the last pandemic. There will be a second one. We don't know when yet, but most probably it will happen someday. And therefore it might be important just to know which potential animal species, we can be the missing link at the moment. So where do these viruses start to appear?
Clear. A question from Jan Taco, I think to both Azra and Sake. Is there a role for citizen science in monitoring the epidemic, or perhaps in other elements that are relevant for helping modeling to curtail this pandemic?
Well, maybe I'll start. I think there's been a huge amount of effort in citizen science already, and particularly with the data collation early on. Many people have become involved in collating information. And one of the challenges we actually have had as scientists working in this field is keeping on top of that information. So summarizing all the research papers, but the pieces of information that are coming out from across the world has been really difficult. So that is incredibly useful. But I think also a citizen science approach to thinking about what is the right approach going forward. Because this is these are societal decisions that are going to affect us all. They're not ones that scientists alone can make, but nor should they be constrained to politicians. I think that information is something we should all be debating.
I have not much to add to that. I like the initiatives of people that use apps to record their behaviors, for example, to demonstrate if there are changes, so that could be included in the modeling, for example. But on the other hand, this may also be a selected group of the population. You don't know what it says about the population as a whole, but I definitely like these initiatives, and you can conclude about possible trends over time, which we could take into account in our models.
Thank you. With that involvement of the public, I will end the public Q&A session. There are still a few dozen questions that are unanswered that we will answer and we will post on the KNAW website. There is something else on the KNAW website that is a very useful resource for people who found this symposium interesting or have other questions. A very accessible document on infectious disease epidemiology with a specific focus on COVID-19. So please do look that up, and please do keep an eye on the KNAW website. It will inform you when we answer additional questions. And with that, I give the word back to my fellow organizer, Cornelia.
Thank you, Teun. Ladies and gentlemen, we have heard 3 brilliant presentations. I think Sake showed us that any epidemic can be modeled. There's always uncertainty, but we should be transparent about that. But that does not imply the modeling cannot be used effectively. I think Bas showed us really open and informative that characterizing the virus genetically can give us a lot of information. Where did the virus come from? Where does it go? Is the local clusters did it come from outside? And which ones are the variants of concern? And Azra, I think, showed us the battle between relaxations of social restrictions and immunizations. And she really highlighted that we will have to be alert for quite some time still. She painted a sobering picture. I think the best case scenario that Azra painted is that there will be still question marks about our long desired international travel and other normal behavior that we will probably not see back too soon, as much as we like it. So she also showed we will not eradicate the disease within soon, most likely, but that does not, of course, imply that we shouldn't try this. If we do not shoot for the maximum, I think we will be even facing more restrictions, more effects on healthcare and our economy. Ladies and gentlemen, I hope you enjoyed the seminar, and I hope sincerely that it did make you more enthusiastic about the work of an epidemiologist. I really hope that all amateur epidemiologists in the Netherlands will start simulating now COVID-19 more seriously. I think Azra gave a perfect link to do so for you. And I really hope that you simply enjoyed also the seminar and its discussions. I did enjoy it very much. And on behalf of Teun Bousema, I really would thank the speakers for the brilliant presentations, and I really would like to applaud them. With that, I thank you for your attention and close this seminar.